Have you ever wondered what exactly happens inside a missile during the first seconds after it leaves the launcher? Most people who observe a missile launch see a column of smoke, a flash of flame, and an object that disappears at extraordinary speed over the horizon or into the sky. What they do not see, because it happens inside a metal structure, traveling at speeds exceeding the speed of sound and lasting only a few seconds before the missile has reached flight conditions radically different from those at the moment of launch, is one of the densest and most violent sequences of physical events that human engineering has ever produced. In those first seconds, more critical systems activate, more extreme physical conditions are reached, and more autonomous decisions are made than in any other comparable interval of time in the operational life of the missile. And understanding what happens in that interval requires examining each of those systems in the precise order in which they come online, because the sequence is not arbitrary. It is a carefully engineered cascade where each event creates the conditions necessary for the next one to occur successfully. The story begins before the missile even moves. In the milliseconds before ignition, the fire control system sends the final launch command to the missile's onboard computer, which at that point has already been running its initialization sequence for several seconds or minutes, depending on the missile type. During this initialization, the inertial measurement unit has been warming up its gyroscopes and accelerometers, bringing them to their operating temperature and allowing them to stabilize so that their initial readings are as accurate as possible before the extreme shock and vibration of launch begin. The onboard computer has received and stored the targeting solution calculated by the fire control system, including the coordinates of the target, the estimated flight time, the atmospheric conditions at launch, and the guidance parameters for each phase of the flight. The fusing system has been armed to the extent permitted by the safety protocols, which in most modern missiles involves a series of sequential arming steps that require multiple independent conditions to be satisfied before the warhead can detonate. All of this happens before a single gram of propellant has been ignited, and the quality of this initialization sequence has a direct impact on the accuracy of everything that follows. The ignition event itself is the first of the cascade of physical extremes that define the launch sequence. In a solid propellant missile, ignition is initiated by an electric current sent to a pyrotechnic initiator embedded in the propellant grain. This initiator generates a hot gas jet that impinges on the exposed surface of the propellant, raising its temperature above the ignition threshold and initiating deflagration across the entire exposed surface within milliseconds. The transition from a cold, inert block of propellant to a fully burning motor operating at design chamber pressure happens in a time measured in tens of milliseconds. And this transition is one of the most carefully engineered aspects of solid rocket motor design. If the pressure builds up too slowly, the propellant may not sustain stable combustion, and the motor will fail to produce full thrust. If the pressure builds up too rapidly, the structural limits of the motor case may be exceeded before the propellant has had time to reach its design burn condition, causing a catastrophic failure. The igniter is designed to produce exactly the right energy input to drive this transition reliably across the full range of operating temperatures the missile may encounter, from Arctic cold, where the propellant is more viscous and harder to ignite, to desert heat, where it may be more reactive than at standard conditions. In the first fraction of a second after ignition, the chamber pressure inside the motor rises from ambient atmospheric pressure to its design operating pressure, which in a high-performance tactical missile motor can be several hundred atmospheres. This pressure rise generates a thrust force that is transmitted through the motor case and the missile structure to the launcher interface, where the missile is held by the launch mechanism. Most missile launchers hold the missile in place for a brief period after ignition, typically a fraction of a second to a few seconds depending on the launcher type, to allow the motor to reach full operating pressure and verify that the motor is producing nominal thrust before releasing the missile. This hold period serves a critical safety function. A missile that is released from the launcher with a motor that is not producing full thrust may not have enough velocity to clear the launch platform safely, and the hold period gives the launcher time to detect a motor anomaly and abort the launch before the missile has moved. In tube-launched missiles, this function is performed by the shear pins or other retaining mechanisms that hold the missile in the tube until the motor pressure has reached a threshold sufficient to break them and allow the missile to exit. The moment the missile separates from the launcher and begins free flight is when the most intense phase of the launch environment begins. In the first half second of free flight, the missile accelerates from zero velocity to speeds that, depending on the missile type, can range from a few hundred to over 1,000 meters per second. The acceleration during this phase can be extraordinary. A shoulder-fired missile like the Stinger may experience peak accelerations of 30 to 40 times the standard gravity during the first second of flight, while larger surface-to-air or air-to-air missiles may experience somewhat lower peak accelerations, but sustain them for longer. These acceleration levels impose mechanical loads on every component inside the missile that are orders of magnitude greater than anything those components will experience during the rest of the flight. The inertial measurement unit, which has to continue measuring acceleration and rotation rates accurately throughout this phase, is subjected to the same shock environment that it is trying to measure, and designing an accelerometer that can simultaneously survive a 40G shock and accurately measure that shock to the precision required for guidance is one of the more demanding challenges in missile instrumentation design. The structural loads during this first fraction of a second are not limited to the axial acceleration produced by the motor. The aerodynamic forces acting on the missile begin the instant it starts moving through the air, and at the velocities reached in the first second of flight, they are already significant. The drag force acting on the nose of the missile and the lift and side forces acting on the fins and control surfaces impose bending loads on the missile airframe that have to be carried by the structural members without exceeding their yield strength. If the missile is launched at an angle to the airflow, which is the case for any shoulder-fired or vehicle-mounted missile that is launched while the launch platform is moving or oriented at an angle to the wind, the angle of attack between the missile axis and the velocity vector generates particularly large aerodynamic side loads on the forward body and nose section. These loads are highest at the beginning of flight when the missile is slowest relative to the aerodynamic forces it is generating, and they decrease as the missile accelerates and the ratio of control force to drag force improves with increasing dynamic pressure. The thermal environment inside the missile changes dramatically in the first seconds of flight in ways that affect multiple systems simultaneously. The motor itself is the primary heat source, with combustion gases at temperatures of 2,000 to 3,000 degrees Celsius flowing through the interior of the motor case at high velocity. The thermal insulation layer bonded to the interior of the motor case absorbs this heat through ablation, sacrificing itself layer by layer to prevent the heat from conducting through the case wall to the exterior structure. At the same time, the exterior surface of the missile forward of the motor is beginning to experience aerodynamic heating as it moves through the air at increasing speed. The nose section, which sees the highest aerodynamic heating rate because it faces directly into the airflow, begins to warm within the first second of flight. For a fast missile, the heating rate at the nose tip during the first seconds of flight can be sufficient to raise its temperature by hundreds of degrees Celsius per second, which is why the nose sections of high-performance missiles are made of materials with high thermal resistance and low thermal conductivity that can accept this heating rate without softening or deforming in ways that would alter the aerodynamic shape and degrade the guidance accuracy. The guidance and control system transition from its pre-launch state to its active flight state happens within the first fraction of a second of free flight. And this transition is one of the most critical events in the entire launch sequence. Before launch, the inertial measurement unit has been measuring the static acceleration due to gravity and using that measurement to determine the missile's orientation relative to the local vertical. The moment the missile begins to accelerate, the accelerometers can no longer distinguish between the acceleration due to gravity and the acceleration due to the motor thrust, and the guidance computer has to switch from its pre-launch orientation mode to its in-flight navigation mode, integrating the total measured acceleration minus the known gravitational acceleration to compute the missile's velocity and position in space. This transition has to happen seamlessly without introducing a discontinuity in the navigation solution that would degrade the guidance accuracy throughout the rest of the flight. Simultaneously with the navigation mode transition, the flight control system begins generating steering commands based on the difference between the missile's current trajectory and the desired trajectory stored in the guidance computer. In the first seconds of flight, before the missile has built up enough speed for aerodynamic control surfaces to be effective, these steering commands may be executed by thrust vector control, deflecting the motor exhaust to generate lateral forces, or by reaction control jets that expel small amounts of gas to generate attitude corrections. The transition from thrust vector control to aerodynamic control as the missile accelerates and the aerodynamic forces become dominant is another critical event that has to be managed carefully to avoid introducing attitude disturbances that could cause the missile to diverge from its intended trajectory. The seeker, which is the sensor at the front of the missile that will eventually lock onto and track the target, has its own initialization sequence that has to be completed within the first seconds of flight. In many missile types, the seeker is slaved to the launch platform's targeting sensor before launch, meaning it is pointing in the direction of the target as determined by the launcher's own radar, infrared sensor, or electro-optical system. At the moment of launch, the seeker is released from this slaved mode and begins searching for the target autonomously, scanning a volume of space centered on the expected target position and attempting to detect and lock onto the target's radar return, thermal signature, or visual contrast against the background. The time required for the seeker to acquire and lock onto the target after launch is called the acquisition time. And minimizing it is a critical performance parameter because a missile that spends more time searching for its target is a missile that has less time to maneuver onto an intercept trajectory. The safety and arming system of the warhead completes its arming sequence during the first seconds of flight. And the design of this sequence reflects one of the most carefully balanced engineering trade-offs in the entire missile. The need for the warhead to be safe enough that it cannot detonate accidentally during handling, storage, or an abnormal launch, balanced against the need for it to be armed and ready to detonate at the earliest possible moment after a successful launch. Modern missiles use multiple independent safety mechanisms that are removed sequentially as the missile satisfies specific conditions that confirm it is in normal free flight. A setback sensor detects the axial acceleration of launch and removes the first safety interlock, when the acceleration exceeds a threshold that could only be produced by a normally functioning motor. A spin sensor, if present, removes a second interlock when the missile's spin rate reaches the level produced by the launcher's rifling or by the aerodynamic spin-inducing features on the missile body. An environment sensor removes a third interlock after the missile has been in flight for a minimum safe distance from the launcher. Only when all of these interlocks have been removed sequentially and in the correct order does the fusing system become capable of initiating the warhead, and even then it requires a specific detonation signal from the proximity fuse or impact fuse to actually fire. The communication between the missile and the launcher, if the missile type supports it, begins immediately after launch and continues for as long as the data link can maintain contact. In command-guided missiles, the launcher's radar or optical tracking system follows both the missile and the target simultaneously, computing the steering corrections needed to bring the missile onto an intercept trajectory and transmitting those corrections to the missile via a radio link or a wire that pays out from a spool in the missile's tail. In semi-active homing missiles, the launcher illuminates the target with its radar and the missile homes on the radar energy reflected from the target, requiring the launcher to maintain continuous radar illumination of the target throughout the missile's flight. In fire-and-forget missiles that use fully active guidance, the data link after launch is not needed for guidance, but may still be used to transmit target update information that improves the accuracy of the initial flight phase before the missile's own seeker has acquired the target. The exhaust plume from the motor, which from the outside is the most visible feature of a missile in flight, has its own complex physics that interact with the missile in ways that are less obvious but equally important to the flight dynamics. The exhaust gases exiting the nozzle at several times the speed of sound create a region of highly disturbed flow immediately behind the missile that affects the aerodynamic forces on the tail fins and control surfaces. At low altitudes where the atmospheric pressure is high, the exhaust plume may be overexpanded relative to the ambient pressure, causing it to contract and then expand in a series of shock diamonds that are visible as the bright and dark bands in the plume. As the missile climbs and the ambient pressure decreases, the plume expands more, eventually filling a cone behind the missile that can be wider than the missile's body diameter. The thermal radiation from this plume is what makes the missile detectable by infrared sensors, and the intensity and spectral distribution of that radiation are what the missile's own infrared seeker would detect if it were looking at another missile from behind, which is why the seeker has to be designed to distinguish the target's thermal signature from the background thermal environment, rather than simply detecting the brightest thermal source in its field of view. What these first seconds of a missile's flight reveal, when examined in the detail that the physics demands, is that the launch phase is not simply the beginning of the missile's journey. It is the most extreme environment the missile will ever experience. The phase where the greatest number of systems have to transition simultaneously from their pre-launch states to their operational states, and the phase where any failure is most likely to be catastrophic, because there is not yet enough separation from the launcher and not enough velocity to recover from an anomaly. Every component inside the missile has been designed and tested to survive this environment and to perform its function accurately in the midst of it. And the fact that modern missiles achieve this with the reliability that operational experience has demonstrated is a testament to the depth of engineering knowledge that has been accumulated over decades of development and testing. In those first seconds, everything that the missile is supposed to do for the rest of its flight is either set up correctly or compromised permanently, and there is no opportunity to go back and fix what went wrong.